Hello, this is chapter 5 on volcanoes and volcanic eruptions. Alright, so as some of you, if not all of you, I hope, should know, on May 18th of 1980, Mount St. Helens, which is in Washington, erupted. So this was the largest volcanic eruption to occur in North America in historic times, and it transformed what was a beautiful looking volcano, kind of iconic if you would, into just a mere remnant of what it used to be. So that day, in southwestern Washington is where Mount St. Helens is located, there was a huge volcanic eruption with tremendous force. The blast blew out the entire north flank of the volcano, leaving just a hole. In a short amount of time, what used to be the prominent volcano with a summit of 2,900 meters above sea level was lowered by more than 400 meters. So just for your reference, 100 meters is about 330 feet or so. So, the summit went from being, close to 10,000 feet to being about 8,500 or 8,800, something like that. So, a very big eruption, obviously. So the pictures that you see above show the progression of the day before the eruption, is the one on the right here. And then to the time that it started erupting on the top left right here. And then the progression as it erupted. So this is early on, first bit of the eruption, you actually see it. And then you see the massive pyroclastic flows that are coming down, the massive ash cloud that isn't really erupting upwards like many of the typical columns that form, but yet it has a lot of volume and a lot of strength behind it. So we'll look a little bit further into Mount St. Helens. So this event devastated a large area of timber-rich land, as can be seen on the picture to the top right. The trees in the area of about 400 kilometers squared were all fallen and intertwined, as you're seeing them in the picture, without any branches. They appeared kind of like toothpicks, as if you were looking at them from the air. So there were accompanying mud flows which carried the falling ash, broken down trees, and water that was saturated with this rock debris for about 30 kilometers, which is close to about 20 miles. So a lot of water that was saturated in the soil and in this ash, making it very dense and very dangerous, as we'll see later on. 59 people died from this eruption. Many of them died from the intense heat and from the suffocation that formed by the ash cloud itself, but some others died from the impact of the blast, and a few others from the accompanying mud flows that I just told you about. Nearly a cubic kilometer of ash and debris was ejected from this eruption, and following the major eruption, hot gases and ash continued to be ejected. The explosion was so violent that the ash column reached about 18 kilometers up in the atmosphere, hence reaching the stratosphere, in fact, not just the troposphere, which is the lowermost layer of the atmosphere, but also the stratosphere, which is the second lowest. Nearby areas received about 2 meters of ash, and crops in nearby states were also damaged, for example, in Montana. States in the Midwest also reported finding some of the ash deposits from this eruption, and nearby towns to Mount St. Helens reported having midnight-like darkness during the middle of the day due to the ash that was covering the sun. And these were big towns like Yakima, for example. They reported this occurring. However, here is a different case. As you're seeing, this is in Kilauea, which is in the main island of Hawaii. Not all volcanic eruptions, as you're seeing, are as violent as the 1980 Mount St. Helens event. Some volcanoes generate relatively quiet outpourings of fluid lava, like the volcanic eruptions that, again, you see in the island of Hawaii. Some other eruptions actually are even more violent than the Mount St. Helens one, although that is one of the more violent ones all throughout. So these eruptions that happen in the island of Hawaii are usually non-explosive, but still bring some fiery displays every now and then, like the fountains that you see in the image to the top right. There has been constant volcanic activity in Kilauea, which is one of the 5 volcanoes in the island of Hawaii, the southeasternmost. And there has been active volcanic activity since 1983. The last time it was very active was very recent in 2018. And what happened is that one of the fissures within this area erupted lots and lots of material. It was active from May through September, or I guess I should say very active from May to September. And a lot of material was ejected, or not ejected, yeah, it was ejected into the island itself. With this eruption, there were many houses, schools, and roads that were damaged. The one in 2018, I should say. And it was interesting that this eruption actually even created some new land within the island. So the lava, as it was flowing and later on crystallizing, reached as far as the ocean in some cases. And so as it was reaching the ocean, it would fall into the coastline and eventually build up on itself until rising above the surface. So it actually built on further land of the island, which is kind of interesting. So the image in the bottom right shows the specific fissure that I was talking about. You see it right here, and you see the material pouring outwards from it. And then in the image to the left, you're seeing the location of Kilauea. The other 4 volcanoes in the main island are Mauna Loa, Mauna Kea, and then I forgot the other 2, but I think we're going to refer to them later, so you'll be able to see them as well. These pictures are all from the 2018 eruption that I was just talking about, from May to September. And it shows the extent and the damage that this eruption caused. For example, here in the bottom picture, you're seeing that the lava is just overtaking this road and is also having some impacts on the electric lines that are running through, on the power lines. In this picture right here, the nature of the eruption in this type of setting is exemplified. I believe this picture isn't from those eruptions that happened last year, but you can see the nature of this type of eruption, where the flows themselves of the lava are non-violent, nor are they too dangerous in the sense that we can still outrun them, but we can see them occurring without fearing for our immediate well-being. Sometimes one of the concerns for our immediate well-being might be from gas aspiration, but even so, in these cases, there's a lot of monitoring, so the students that you're seeing in the picture wouldn't be allowed to do this if it wasn't safe. So, as we saw in the last few slides, there are different types of eruptions. The typically known, more violent, cone-shaped explosive eruption, but also a more quiet lava flow. One of the main factors influencing the type of eruption is the magma type as the source for said volcanic eruption. Recall that magma is going to be the parent material of igneous rocks, and it is molten rock that may contain some solid crystalline material and also contain varying amounts of dissolved gas. These gases typically just water vapor and carbon dioxide and sulfur dioxide. If this magma erupts at the surface, then it is called lava. So if you remember from chapter 4, we discussed that mafic igneous rocks typically contain greater amounts of ferromagnesian silicate minerals, which makes them darker in color and also heavier in weight. By contrast, the more felsic igneous rocks typically contain greater amounts of non-ferromagnesian silicates, so they are lighter in color. Intermediate igneous rocks have a mineral composition in between felsic and mafic rocks, as should be expected. The figure in the slide is fantastic for us to see the different properties from each of the types of magmas. Here we can compare the silica content, the gas content, the eruptive temperatures, the viscosity, the tendency to form pyroclastic material, and the types of landforms that form from the different types of eruptions based on the magma type. As you can see, the more mafic magmas have the lowest silica percentage, the lowest gas content, or the least gas content, I should say, and erupt at the highest temperatures. All of these factors make the flow to be quite fast. So all of those, low silica, low gas content, and high temperatures make the flow be fast. And by flow being fast, that means that viscosity is low, as we had discussed in chapter 4. In contrast, the more felsic magmas have the greatest silica percentage, the greatest gas content, and erupt at the lowest temperatures. Again, all of these factors make the flow be very slow, which means that this melt is going to have a very high viscosity. So, I don't know how to help you memorize this, but you gotta know that if there's high silica, high gas content, and low temperature, that means that the viscosity is going to be high, or that the flow is going to be low. I guess all of those things are related. You could come up with some sort of mnemonic device to help you with this. So in the case of the felsic magmas, again having this very high viscosity, it also causes the magma to build up a lot of pressure due to the gas content and the low flowability inside of this melt. So once this pressure builds up enough, we get the violent explosive types of eruptions characteristic of these type of felsic magmas. And that is also why they bring this great amounts of pyroclastic material with their eruptions. And we'll talk about that later on as well. Remember from last chapter that more mafic magmas usually resemble mantle composition and are usually originated at the asthenosphere, with the magma rising towards the surface due to its low density. The areas where they are more common is at seafloor spreading and over mantle plumes as well, which are hotspots as a surface expression, right? When you have that mantle plume rising upwards toward the surface, and it actually does create a surface expression, such as a seamount or a volcano, then you get what we name hotspots. More felsic magmas, by contrast, usually resembles the crust composition and are either at the boundary of the asthenosphere and lithosphere or below, but having undergone assimilation of the overlying crustal rocks. The areas where they are more common is typically at continental settings, so at subduction zones or where crustal rocks are heated enough to melt onto the magma body, and then be incorporated within that melt, hence making it more crustal resembling.